Well, it's been a long afternoon, and I'm between you and break and networking, so I'll try to keep this moving. I'd like to start by thanking Bill and the DARPA team and the DoD and the US government for allowing Cadence to be part of the ERI program. We're honored and we're challenged by it. And we too believe it's more of a journey rather than an endpoint. And I'd like to explain a little bit about that. So I lead the custom IC package, and PCB R&D teams at Cadence. We have about 1,200 engineers, electrical engineers, computer scientists, technologists, and increasingly a number of mechanical engineers in our team, and you'll understand why in just a few minutes. Like Erica, like some of the other speakers, I'll talk about some technology trends, about Moore's Law a little bit, about the world beyond Moore's Law. But I also want to talk about how do companies like Cadence, commercial companies, work more effectively with government agencies, and how do we work more effectively with semiconductor companies and with the defense aerospace ecosystem in this new technology revolution that's unfolding. So I've been lucky to have a long career working indirectly on a lot of stuff related to the US government and directly on a number of programs. When I started my semiconductor career, it was at Harris in Melbourne, Palm Bay, Florida, about 30 miles south of Cape Canaveral. We did a lot of rad-hard ICs for NASA's Space Shuttle program and military communications and for satellite systems. I left Harris in the late 80s, started at an EDA company called Zynetics, and Zynetics had one small DARPA contract. We used Fast Henry and Fast Cap for DoD applications out of MIT. That company was bought by Avanti. I was there for about a year and a half, and then went to Pittsburgh, to Carnegie Mellon University, and did a spin out of some long-standing technology related to analog automation. So basically, place and route and analog at the IC level, and circuit sizing with SPICE in the loop. And that company was called Neolinear. Neolinear in 2002 was part of a contract called NeoCAD. It was a top-down RF synthesis flow funded by DARPA, funded by the DoD, working with Boeing, MIT, and Carnegie Mellon. Neolinear was acquired in 2004 by Cadence, and I've been at Cadence for 14 years. And in the last 5 or 6 years, we've had a lot of activity in the space with DoD, with DARPA, and I want to share some of those stories in just a minute. And one interesting thing, when I joined Harris in 1981, of course, in the middle of Moore's Law, I think they were called the classic days by one of the speakers, our social security numbers were our employee ID numbers. So things were not quite secure, even though we worked on a lot of black box programs. So if you were from Pittsburgh, and if you were affiliated with Carnegie Mellon, you knew a lot about what was going on in the autonomous vehicle grand challenge in 2004. If you followed it in 2004, every vehicle crashed or burned or failed within sight of the starting line. No cash prize was awarded, no winner was declared. But when the dust settled and the smoke passed away, that community of technologists and engineers believed that the driverless vehicle was possible. Now, shown here is the poster for the second grand challenge on the autonomous vehicle front. And in 2005, October, more than 23 vehicles entered the competition from various teams to go more than 100 miles in desert terrain. The winner was the Volkswagen Stanford team. It was a close finish. 5 vehicles actually finished the entire course. Shown here is one of 2 vehicles from Carnegie Mellon University that came in second and third place. And this is the red team vehicle, and it was led by a guy named William Red Whitaker. Bill Whitaker, a long-term roboticist at Carnegie Mellon. Bill's a really interesting guy. He spent 20 years earlier, he started his robotics career working on robots to look at reactor number 2 of 3 Mile Island with the partial meltdown. The secret sauce in these days was taking that sensor data and using algorithms and software to translate that into driving instructions. Note the impressive roster of technology companies, hardware, software, that were involved in making this vehicle in a second place finalist in that year. The DARPA program, that grand challenge in 2004 and 5, it was about a leap in technology, no doubt. But I would posit to you that it was as much about a leap in imagination, in collaboration, and in confidence to take that big step. Before I go on, let me tell you just a little bit about Cadence. I'm not going to do a marketing review. We're about 7,000 employees. We do a couple $2 billion a year in revenues. There's one thing that Cadence gets regularly criticized by Wall Street for, and that's that we invest too much money in R&D. Now, those of us on the technology side believe it's mandatory, given the inflection point that we're in right now. 40 cents of every dollar gets plowed back into R&D. In fact, with 6,000 of our 7,000 employees as technologists and as engineers, it's no wonder that we have been voted a top place to work 4 years in a row by Fortune 100, not only in the US, but across the globe. We love challenges like 3-nanometer design. We love the world of more than more that's unfolding. So you hear a lot of words bantered around today: a data-driven economy, Industry 4.0, a fourth industrial revolution, a smart product world. There is an inflection point. We all know it. That's why we're here. I'd like to look at a couple recent headlines, but I think we all can watch our homes transforming, our automobiles transforming, our workplaces transforming. When you think about it, in 2017, the semiconductor industry had its strongest growth rate in revenues in about 15 years. This is on the biggest base of revenues it's ever had. 23% beyond, in fact, would have been even larger, except for there were a number of customers on allocations. There were severe shortages, especially in RF communication modules. There's a reason for that. We'll get to that in a minute. And already forecasts for this year are back up in the double digits. Now, we know that there's a lot of applications unfolding for new ways to use semiconductors, whether it's smart devices like Google Home or Alexa, the autonomous vehicle, IoT devices, and more. And we know that networks are changing. One of our speakers talked about that. And at the same time, there are a whole bunch of technology challenges, which is why we're here. So I would posit that it's all about this fusion of advanced electrical technology with advanced mechanical, layering in RF communications capability or millimeter wave capabilities, along with sensor data and quite a stack of software. And then taking that fused product and connecting it into the fog or into the cloud. It may be ultra low power at the edge and intermittently sending up data, or it may be standalone and very powerful at the edge. Now, this is a massive disruption, not only to semiconductor companies, but to every system company in practically every vertical. They're all stepping back. I deal with a lot of companies. They're asking themselves, what does it mean for us to thrive in a smart product world? And they're literally throwing out their current development plans because they don't want to be pushed away by a startup or pushed away by a competitor. If we look at the world of automotive, maybe one of the fastest transforming right now, how many people here really think that 5 to 10 years from now, it's going to be Toyota and GM and VW and Honda and Ford and Nissan again? In a world where data matters, in a world where software is paramount, in a world where systems matter that fuse these technologies. Might it be Google or Uber or Baidu? These companies are unfolding, and like in my hometown of Pittsburgh, Uber is a big player in that market. Now, while all this is going on, there's been a massive consolidation on the semiconductor front over the last decade. And the resulting companies are also having to deal with this more than more world that's unfolding. Their customers want this fusion of technologies as the foundation for the next generation product. And last but not least, we have China. And China's not investing tens of billions of dollars, but hundreds of billions of dollars into new foundries, into semiconductor companies, and into electronics. And so I would posit that why we're here today is as much about how does the US government, how does our society, how do democracies across the globe not replicate that investment, but harness the power of commercial companies by collaboration, by teamwork, and by investing strategically. People have talked about it. We know that we've been very successful in my 37 years in semiconductors by shrinking interconnect and shrinking transistors. But we know that it's slowed quite a bit in recent years, and that we're getting to the atomic scaling limit of CMOS that's been talked about. And therefore, new materials and stacking and multi-die and multi-technology are all unfolding for that world of more than more. Now, the world of electronics is making a massive disruption inside of the world of manufacturing. And large global manufacturing plants in time are going to give way to much smaller, localized manufacturing plants. These will produce products on demand that are customized using 3D printing and a lot more robotics. And this will include printed electronics. And this world is another one we have to plan for. And so within the world of Cadence, we started brainstorming this and what impact it would have on our business, Industry 4.0, about a decade ago, because we do everything from IP through the chip, through the package, through the board, even including the mechanical enclosure and how you analyze that entire system. And so we call that system design enablement. And so we have tools at all of these various levels, lots of verification, even hardware accelerators and emulation. I'm not going to go through the list of tools. I'll show you a little bit of that in a minute. But even beyond this, we asked ourselves, what does our ecosystem need to look like? I think just like the DARPA and the government agencies are asking themselves, who should be involved today? And we went beyond the classic foundries. We went beyond the classic IP companies. Of course, they're still partners and EDA partners. But we went into a world that's different for us. So today, Cadence sits on standards committees in automotive, in medical, industrial. We're in functional safety committees like ISO 26262 for ASIL standards for the driverless vehicle and more. 3 years ago, we launched a strategic partnership with MathWorks to bring the system level world inside the detailed electronics transistor level world. And so today, Simulink is integrated with our board level simulator, PSpice, and I can do simulation of dynamic systems. We have MATLAB integrated into our Virtuoso Custom IC environment. I can do data analytics. And I can bring system level models right into the transistor level world. Just a few weeks ago, we announced a new partnership with National Instruments, and this one has two major focus areas. The first is on the world of 5G and millimeter wave design and technologies, and the second is on enhancing design for test. So whether it's at the chip, the package, or the board, or the system level, what you design and simulate is very close to and highly correlated with the actual lab results. We have a lot of technologies, a lot of products, but we don't believe that's where we need to go. We believe we need systems, solutions for this fusion of technology. So as an example, last year we introduced a product called the Virtuoso System Design Platform, VSDP. And while my chip is still open, my custom IC is still open, I can import actual package parasitics, actual board parasitics, so I can understand the performance of the entire system, not just the chip itself. I can do smart I/O planning across those various fabrics and smart route planning across them. In fact, this won the 2017 Product of the Year Award by Electronic Products. If you believe there's a revolution unfolding, if you believe there is a fourth industrial revolution, just wait for 5G. Now, it was talked about a little bit before, but in the first phase definition, we will be 40 times faster than 4G with much higher bandwidth. This will be the foundation for the driverless car, for the smart city, for the smart home, office, and more. And these networks will start to roll out in volume in 2020 and will work alongside 4G and 3G technologies. It's not for the faint of heart. Select technologies like silicon photonics, like wafer-level packaging, prerequisites in this space. The first definition of 5G was just published in December of 2017, and more definitions are unfolding. There are more questions than answers right now. It will support upwards of 50 gigahertz in terms of the spectrum, unlike 6 gigahertz for 4G, where it topped out. Analog beamforming will be supported. 5x bandwidth increase in the first phase. Now, to design those type of systems, especially the RF modules and the RFICs, we're going to have to integrate the antenna arrays with the transceivers, with the power supplies to minimize system loss. We don't even know yet how we're going to test that. It's not going to be cabled. It's likely to be over the air. Maybe that partnership with National Instruments makes a little bit more sense. We have to team and think differently. Let's talk just for a minute about robotics. So 4 years ago, the country of Japan and the Ministry of the Interior there came out and published something called the New Robot Strategy. It's been a huge success. And if you go to Japan today, I was there actually 2 days ago, there's optimism like there hasn't been in over a decade. And if you look at this, 3 out of every 4 robots manufactured in Japan were exported in 2017. It increased their exports by 11%. That's a huge number, a huge number. Now, part of this, of course, is driven by Japan's prowess in automotive manufacturing. But it's driven by 2 other things that are equally important: an aging population. And they want robots in the home to assist their senior citizens. The second part is a shrinking workforce. They're not going to open up their doors wide open, and so they're going to have to be globally competitive with a lot more automation. Now, to give you a sense of the size of this segment, it was $40 billion in 2017. In 4 years, it'll approach $250 billion. That's a pretty smart bet. It's an inflection point that's unfolding. So let's talk a little bit about spatial perception, which is key to robotics. It's key to the world of the driverless car. So what's shown here is basically a camera module, an advanced camera module. I've taken the chassis, I've broken it up into 2 parts. The first part has the lens and the image sensor and related electronics. The second part has the Ethernet interface and the Ethernet cable out. Now, that mechanical unit is constructed with another new partner from Cadence, like Dassault Systems, or like Autodesk, or like Parametric Technologies. They were not partners before. They're partners in our new world. On the top left, we see that image sensor board with that large CMOS image sensor, and below it we see the main board. Now, these are designed using rigid flex technology, using our Allegro PCB design tool, and they're connected with that flexible technology, and then they're put inside that cabinet. Now, you know when you do that, we have to worry about thermal, right? And so we have to, and we know as temperature goes up for those sensitive electronics, resistance goes up, I have problems with power leakage that are going to unfold. So we have to balance current density with the thermal temperature. And so we have to simulate both, and we do that using our power DC technology. I also have high-speed components. I have DDR4. I have DDR5 that's going to unfold in one of these very soon. And so I have to worry about eye openings. I have to worry about signal integrity. So there we use more analysis tools like our Power SI technology. I have to worry about electromagnetics. There we use 3D EM, putting this all together. So we talked about the DARPA Grand Challenge in 2004. Let's fast forward 12 years. So shown here is a Uber test vehicle on the streets of Pittsburgh, with Pittsburgh in the background. There's 80 of them, 82 in fact, driving around the streets of Pittsburgh. Uber started by hiring 42 professors out of Carnegie Mellon. That didn't go over very well from both the robotics and computer science departments. The one thing you'll note on this test vehicle from 2016, it's got a very large LiDAR unit on the top of it, that rotating mechanical beacon. And what that does is it gives you that 3D vision of what's happening around the vehicle, and it's supplemented with radar technologies and camera technologies. But that unit costs more than the vehicle below it. And by the way, its expected life is 4 years. That's not going to match well with a driverless car. And so what happens? There's commercial innovation, which is why we're here today. How does DARPA, how does the US government tap into it? And soon, just like that camera module I showed you, which is based on a real design, is going to be in the headlamp of that car. Right? That's in 3 short years, a massive transformation unfolds. So how do you design something like that? So I would posit, one of our speakers talked about wireless technologies. They are permeating the automotive ecosystem. So of course you like Wi-Fi and Bluetooth in the car, and all new cars have that, and we take advantage of it. There are hidden wireless technologies. There's drive-by wireless technologies. Your steering wheel is not connected to the axle. Sorry, that stopped a long time ago. And there are Ethernet technologies. They're taking cabling out of the vehicle, increasing functionality by a lot. But for the driverless car to be successful, we're going to need to get, at a minimum, 25 gigabits of data in and out of that vehicle per hour. That means silicon photonics in the cloud. It means silicon photonics in that LiDAR system in the car itself. So to do that, multiple companies are using this very flow here, and I just wanted to kind of highlight it. I won't go through the details. But inside this Cadence custom IC platform, you can do the chip, the package, and the board design. You can design the digital and the analog for the mixed signal IC. You can co-design the electronics and the sensors for all those MEMS mirrors for that LiDAR unit. You can co-design the photonics and the electronics inside of the same unit. You can import the mechanical enclosure and do a full analysis of the system for power, signal integrity, thermal, electromagnetics. You can even import, with our partnership with MathWorks, a beamforming algorithm toolkit into that custom IC environment. So that's a picture of next generation flows and next generation collaboration happening at the commercial level. So we're privileged to have a lot of customers in the defense and aerospace business. I will tell you that I think, Bill, we met maybe 4 or 5 years ago, and we started talking about Cadence was maybe much more on the periphery than, how could we become more involved? Just like we help every advanced smartphone company come out with their next chip and their next boards for their advanced smartphone, why can't we help the US government with better SoC design, with a shorter verification cycle, with more reuse and more modularity? And with that, over the last few years, we've had the privilege of being involved in more programs, some from DARPA, some from AFRL, and other agencies. So this is highlighted in the 2018 National Defense Strategy as a key pillar. And I'll just read it briefly. So platform electronics and software must be designed for routine replacement, or I would say update, instead of static configurations that last more than a decade. And of course, they must deliver the performance when it's needed. So what unfolded from all of this are a number of programs where Cadence has gotten more involved in a collaborative effort. Now, I will tell you, our business model, my group alone is 1,200 engineers. The money from these programs is not what funds us. I can guarantee you that. 40 cents of every dollar of revenue funds what we do in R&D. But what I like about these programs is they force us to think more about research. We tend to get involved heavily in incremental development, and so that's really valuable for us. It partners us, forces us to get out of our comfort zone, to talk to academic institutions even more than we do today, to talk with semiconductor partners, to talk with DoD, ecosystem partners. So for instance, we're part of the CRAFT program working with UC Berkeley and working with Northrop Grumman and BAE Systems on how to reduce that SoC design and verification time, not by a little, but by a lot. And we're part of that More Than More program of 2.5D modular design for heterogeneous design. And SHIELD is interesting, not because it's the smallest IC, that's interesting, but because of the design data analytics that can allow you to ensure that the military electronics are genuine, where we start entering the world of artificial intelligence, machine learning, and deep learning as part of the system itself. We are modifying, adapting a lot of Cadence products. These are just a few as part of these programs, so they're more applicable to the defense and aerospace industries and to the needs of the DoD. There's little doubt that the government has tons of chips, packages, and especially boards that need to be updated. We all know that, right? But if you've ever done board design, it's not like board design 30 years ago. It's very complicated. It's very hard. And all those trade-off analyses that I referred to earlier talk to that. And so I think we're here today because ERI, the Electronic Resurgence Initiative, is key to this concept of integrating universities and leaders in defense, aerospace, and semiconductor in this world of machine learning to bring more intelligent design. Now, to be fair, Cadence has been working on this for a long time. We're not waiting on DARPA. We can't. We're driven by commercial customers who push us to the edge every day of every year. And so we've been working on machine learning algorithms. One of our products, that Virtuoso Custom IC product, it's been using machine learning algorithms for 5 years, commercially, in volume. We have parallelized all of our algorithms that make sense for this world. We put in analytics, we put in optimization. So we're honored to be part of the ERI program. We're pleased that our majestic proposal was selected, and I would encourage you to attend David White's session tomorrow when he's going to talk a little bit about what we're doing in terms of machine learning and deep learning. In my group alone of 1,200 engineers, we got about 30 engineers working in machine learning, have for years, been working on this front. We'll be supplementing it now in light of this program. I had to write out what this is because I couldn't remember it. It's machine learning driven automation, automatic generation of electronic systems through intelligent collaboration. That was David White, the engineer, as a marketing hack, coming up with that name, I suspect. We don't want to change the way people do design. We want to work with the same inputs you would work with if you're doing your chip design. For instance, your PDKs, or your schematics, or your constraints, or your simulation models. We want to utilize those. And as you enter that package and board world, we'll look at the die abstract, and we'll look at parts libraries, and we'll look at outlines for those packages and those boards and weave those together. We're not, of course, going to exclude the engineer from the loop. We want the engineer to be presented with placement variants, with routing fabric approaches, and to make selections. And as the engineer or the designer makes selections, the system's going to learn, and it's going to learn, and it's going to get better, and it's going to get better, and you will own that data, and it will be your data. And that's a critical component here. Now, we are very privileged to be starting with a number of key partners, and I think this partner list will grow over time. I would argue that NVIDIA, with their GPU and related technologies, have really been a major catalyst for the resurgence in artificial intelligence and machine learning. And we're pleased to be working with Carnegie Mellon University. One, we know them well, but secondly, if you think back to the 1960s, Nobel Prize winner Herbert Simon was there doing a lot of advanced work back in the 60s on AI, not only there, of course, but at MIT as well. So in summary, our goal is to work cooperatively with the greater ecosystem, the academic ecosystem, the government agency ecosystem, the semiconductor ecosystem as part of this, whether it's at the IP level, the chip, the package, or the board level. This will cross into the world of software and security. It's going to cross into the world of mechanical. It's going to cross into the world of test and measurement and enterprise and more. And just like that DARPA challenge of 2004 and 2005, it's more than just a leap in technology. It's a journey. It's a journey. It's also a grand challenge that's unfolding. And we believe it will help us build confidence, collaboration, and imagination. Thank you very much.